Hi all. In this video we discuss section 20. The last class we have seen Taylor's theorem. If a function f is analytic at z0, then Taylor's theorem asserts that there exists a power series expansion for that function f in terms of the ascending powers of z minus z0 starting from 0. But if that function f fails to be analytic at z0, we cannot apply Taylor's theorem for that function. In that case, we use this theorem, what we called Lorentz theorem. Suppose that a function f is analytic throughout an annular domain R1 less than mod z minus z0 less than R2. So that is this annulus region. In this region, we can assume that that function is analytic, even though that is not analytic at z0. Then in that case, this annular region is about this z0, and let C denote any positively oriented symbol close to contour z0 and lying in that domain. So domain is in fact this annular region. So if you consider any symbol close to contour lying inside this annular region, then at each point in the domain f of z has the series representation. So this is not at all power series. This contains, or this series may contain, a positive power of z minus z0 as well as negative power of z minus z0. So f of z can be expanded using two parts. So one part contains only positive, non-negative powers, and the next part contains negative powers. So this f of z is equal to summation n equal to 0 to infinity a n z minus z0 all raised to n plus summation n equal to 1 to infinity bn upon z minus z0 raised to n in this annular region. Then the coefficients of that series can be obtained using these two formula. An is equal to 1 upon 2 pi I integral over c f of z dz whole divided by z minus z0 to the power n plus 1. N varies from 0 to 0, 1, 2, 3, etc. That is, this an is in fact the coefficient of the non-negative powers of z minus z0 in that Lorentz series, and bn can be obtained using the formula 1 upon 2 pi I integral over c f of z dz divided by z minus z0 to the power minus n plus 1. N varies from 1, 2, 3, etc. So these bn are the coefficients of the powers of z negative powers of z minus z0 in that series expansion. So in this case, we expand, or we use the expansion of a non-analytic function at z equal to z0 if it is analytic inside an annular region, or if we remove a neighborhood containing z0, then if that function is analytic everywhere else, then we can use this formula. So in our syllabus, we will not consider the proof of this Lorentz series, so we are not going to prove all these things. And our next, so you just remember that series, and we can, if we can go through some examples, then we can easily understand what is the purpose of that Lorentz series. We know that the e raised to z is an analytic function, so you can easily expand this e raised to z at z equal to 0 using Taylor series or Taylor's theorem. So the Taylor series expansion of e raised to z is equal to 1 plus z by 1 factorial plus z square by 2 factorial plus etc. So the region of validity of this series expansion is whole of the complex plane, that is mod z less than infinity, because e raised to z is analytic everywhere in the complex plane. But if you consider the function e to the power 1 by z, that we cannot apply Taylor's theorem for this function at z equal to 0, because at z equal to 0 this function e raised to 1 by z is not analytic. But we know that the only singular point for this e raised to 1 by z is z equal to 0. So if you remove a neighborhood centered about z equal to 0, then the rest of the places in the complex plane, this function e raised to 1 by z is always analytic. So this e raised to 1 by z has a series expansion as well. So that expansion contains the negative powers of z minus 0 or z negative powers of z as well. Therefore, we use the Lorentz series to get that expansion. So e raised to 1 by z can be expanded in this way. Okay, so this expression, we use the same expression of Taylor series by replacing this 1 by z by this 1 by z. But the only difference is this expansion is valid for every complex numbers mod z less than infinity. But in this case, this expansion is valid only for the complex numbers which is not equal to 0. So this expansion is valid only for the region 0 less than mod z less than infinity. This is obtained using the Taylor's theory, using this expansion. This 1 by, whenever 1 by z is less than infinity, then only this Taylor's this expansion valid. Or the other way you can think of the Lorentz theorem, which says that if this function f of z equal to e raised to 1 by z is analytic except 0, then there is a Lorentz series expansion for that function. So this is the Lorentz series expansion of e raised to 1 by z. Similarly, there are some examples are discussed in after this one, that is f of z equal to 1 by z minus I whole square. This 1 by z minus I whole square is equal to, this is sigma n equal to minus infinity to infinity cn z minus I whole raised to n. That is, we expect a series expansion for this function. We know that this function is not analytic at z equal to I. Then if you remove that I or from the region, or you consider an annual region which does not contain this I, then in that region there exists a Lorentz series expansion for this function. Okay, so the Cn is obtained by this formula. So we combined an and bn to write this expression, or by putting c minus 2 is equal to 1. And these are the formula for obtaining the coefficient. So if you know the coefficient of, we know that b1 is equal, in the former case we consider this function e raised to 1 by z. We know that this can be written as 1 plus 1 by 1 factorial into z, 1 by 2 factorial into z square plus etc. So we know that this is in fact a naught, and this is b1. This coefficient of 1 by z is called b1. The coefficient of 1 by z square is equal to b2. So this here we know that a naught is equal to 1 in fact, but b1 is equal to 1 by 1 factorial. b2 is equal to 1 by 2 factorial. b2 is the bn is the coefficient of the negative powers of z minus 0. So if you use the Lorentz series or Lorentz theorem, we can say that b1 can be obtained using the formula 1 by e to the power 1 by 2 pi I integral over c e to the power 1 by z dz is equal to b1. But from this expression you can easily evaluate what is b1. b1 is 1 by 1 factorial. Therefore you can write 1 by 1 factorial is equal to 1 by 2 pi I integral over c e raised to 1 by z dz. So we use the Lorentz series or Lorentz theorem to evaluate this integral as well. Lorentz theorem says that the coefficients of the Lorentz series expansion can be obtained using some integral. But other use of the theorem is to find the value of this integral using that series. Okay, so if you b1 is known, then you can easily evaluate what is this integral. Okay, since this b1 is 1 by 1 factorial, which is in fact 1, you can easily evaluate this integral using this using the value of this b1. Okay, so this is the other use of this Lorentz series expansion. Similarly, you can write Cn is equal to this. Once you know the Cn, then you can easily evaluate this integral as well. Otherwise, you can use the other formula. You can the other way to evaluate the coefficients using integral. If this integral is easy to evaluate, then you can easily get the coefficients of Lorentz series. So these are discussed in this one. To how to expand a function to get the Lorentz series expansion. is the next example. So once you have a function like this, the representation, suppose we have three regions, d1, d2, d3. D1 is the inside this mod z is equal to 1, that is inside this inside the first or inner circle, and that is this one. This is the region d1, and d2 is the anal region, and d3 is outside this. Okay, so if we have three different regions, then our aim is to find series expressions for, or series expansion of a function f of z is equal to minus 1 by 1 minus z plus 1 by 2 times 1 by 1 minus z by 2 in each region. Okay, so find out the expansions of f of z, which valid for d1 and which valid for d2 and which valid for d3 as well. So we consider these are the three distinct questions. So you can go through these examples, example 3, example 4, etc. So in these examples, they consider the series expression of a function which valid for a region you have given. So this is the section 60 and 62. Then with this we can conclude module 3. So in the next class we will discuss section I think the chapter 6, which deals with the residues and poles. That is going to be in the module 4.